the exercise. One. Then we have that the policy, the velocity of the point P can be written by the following, that V P is equal to V absolute Vf, or frame velocity, plus V relative. That it means here what we have always the absolute velocity. This absolute velocity, it belongs to the fixed coordinate system x, y, and z. That is means has two terms. This terms is called the frame velocity, which is for the whole system, and the velocity relative. The velocity relative, it belongs to a relative coordinate system, x prime, y prime, and z prime. Okay? Now, if we take this, what we have, the whole system is rotating with the angular velocity omega 1. And the system, or let's say the disk D, it's rotating with the angular velocity omega 2. Okay? Now, if I write the equations, what we have here, Vf is equal omega 1 cross R. That it means that R here, it's always we have the following relation. Omega, it depends in which coordinate system we are, either the absolute coordinate system or the frame coordinate system or the relative one. And we have also V relative. This is equal to omega 2 cross one moment. We have omega 2 cross R2. Okay. Now, omega 2 corresponds to the angular velocity of what? Of the disk D. Omega 1 corresponds to the angular velocity vector of the whole system. That is, means the arm is rotating with omega 1. Yeah, rotating also with the disk. Yeah. Now the R and R2. This are only the vector position relative to the coordinate system x, y, and z. Yeah, and R2 is the distance, the vector, yeah, position of this disk where we have here R2 is relative to the coordinate system, the relative coordinate system, x prime, y prime, and z prime. Now, if I express this, what we have here, we have the f as vector is equal to here omega 1 cross r. And what we have omega 1, it's rotating in the direction y, okay, in positive direction, okay. That it means if I show myself, yeah, and I think this is, you should have done it in mechanics 1, when you calculate the moment, yeah, of any system, what we have here, we have the vector omega, it's rotating like this. Okay, I don't know if you see my hand. Yeah, it's rotating like this. You take your finger, it's show the direction of the vector. Okay, and the vector now, if you take omega 1 like this rotating, now my finger here show the direction which is along y direction. And there is no x direction and z direction. That is means now, if I write here the component of it, there is 0 in x direction, there is omega 1 in y direction, and there is 0 in z direction. This is cross. Now I take the position of P. Here we see in x direction relative to the coordinate system x, y, and z, there is the distance of L plus R cosine alpha. Okay. In y direction, there is only R sine alpha, and in z direction, it's 0. Okay. Now, if I make this cross product, okay, maybe some, they don't know how to do this. As I said, I'm not doing mathematics. You neglect for the first component, that it means how we can get now the vector. When I make the cross product, what we have, you delete the first line and you have omega 1 multiplied by 0 minus r sine alpha multiplied by 0. Then you will get here, first component is 0 in x direction. Now, if I want to calculate the second component, I neglect this one, second line, okay, or second component. what I do, it's 0 multiplied by 0 plus minus L plus R cosine alpha multiplied by 0. Okay, then you make only the cross. Okay, now only the second component. It's not like the first and the third component. The whole term here, 0 multiplied by 0, this is between, yeah, bracket, you have to do the minus sign, okay? Either you do the following with minus sign, or instead you make like this, okay? Start with the third component, the first component, L plus R cosine alpha multiplied by 0 minus thus this first component multiplied by the third component, okay? Then I will get also here for the second component 0. Now, if I want to calculate the third component, I neglect the third term here, and I have 0 multiplied by R sine alpha minus omega 1 multiplied by L plus R cosine alpha. Then I will get here minus omega 1 multiplied by L plus R cosine alpha. Okay, this is the expression of VF. Okay, now coming to the expression of VP here, V relative, yeah, it's omega 2 multiplied cross R2, okay? Now we have V relative it's equal to now the component of omega. What we have omega 2, it's rotating in Z direction or Z prime direction. Yeah, it's opposite to the opposite from omega 1. Then it means what we have 0 x direction, 0 for y direction, and here omega 2. And here cross the component of R2. This is, as I said, it belongs to the relative coordinate system x prime, y prime, and z prime. What we have here, it's only the projection of R along here, the x prime, y prime, and z prime. Then we have R cosine alpha. We have the second here, R sine alpha, and in z direction it's 0. Now, if we look to the vector product, as I said, we eliminate the first line to get the first component. Yeah. Here, then to get the first component, as I said, we eliminate the first line, then we have 0 multiplied by 0 minus omega 2 R sine alpha. Yeah. Then here, minus omega 2 R sine alpha. Okay. Now, if I take the second component, we eliminate this line here, second one. Then we have 0 multiplied by 0. Yeah. Or this is, we said, if we start from here, from the link part, link vector, 0 multiplied by 0 minus omega 2 r cosine alpha. But all things, yeah, it's with minus sign, yeah. Then it means it will become here omega 2 r cosine alpha. And the third component, as you can see, yeah, if we eliminate this, the third line, yeah, we have 0 multiplied by this r sine alpha minus r cosine alpha multiplied by 0, then it will give 0. Okay, now if we want to determine now Vp, the velocity of the vector of the point P, I have to make only the summation, then it means I will get minus omega 2 r sine alpha and we have omega 2 r cosine alpha and we have for the third term minus omega 1 L plus r cosine alpha. Okay, this is now Vp. That is means we have only the sum of Vf, the vector, the frame velocity plus the relative velocity, and we have only to add the first term with the first term from this one, second with the second, and the third with the third. Okay, then we get the velocity of Vp. Yeah, this is the expression now. This is the velocity, the expression for what it's asked for the first question. This is now the expression for Vp. Okay, as I said, yeah, this morning and the previous times, if you have questions, let me know. Yeah, but please repeat each exercise at home. Yeah, that you know, that you understand the mechanism. Compare always the equation that we got from the lecture and how we use them, yeah, in the tutorials. Now the second questions is here. Now the second is to determine acceleration here A of the point P as vector. Okay, this is what it's asked for. Now what we have, we said that AP also, but this is different from the velocity. Velocity has always two components, the frame velocity and the relative velocity. But the acceleration has three terms. Yeah, the frame one, the relative one. Additionally, there is the what we call the Coriolis velocity, that acceleration. That is means we have a f plus a relative plus a Coriolis. Okay, this is what we have, the three terms. Yeah. Now we call it here with, by definition, return back to slides. Yeah, each term is defined as follows. That we have AF, the frame one, it's equal to omega 1 as it's the frame angular velocity, omega 1, yeah. This is dot, that is means the omega 1, the angular velocity, cross r plus omega 1 cross omega 1 cross r. Okay, this here, this term here is only VF. Yeah, as you see it here, VF, it's only omega 1 cross R. Yeah, and this is here VF is this term. We can write it also as omega 1 cross VF. Okay, VF will have its expression. Now, if we take here AF, what we said in the exercise, that omega 1, yeah, that the arm rotate with constant angular velocity omega 1. If it said it's constant angular velocity, that it means its time derivation, omega 1 dot, will be equal to 0. Okay, then it means we have here these terms here will be equal to 0. Okay, then we have only the second term here. Yeah. Now, if we make AF, this is will be equal to vector here, or I simplify it now that we will not lose the expression or the way that it's here VF. Okay. Then we have here omega 1, as we said, it's only 0 omega 1 value, yeah, magnitude 0 cross the expression of v frame, the frame velocity. Then we had, or we found that it's 0, 0, and minus omega 1 L plus R cosine alpha. Then if we make now vectorial product or cross product, we will get here minus omega 1 square multiplied by L plus R cosine alpha 0 and 0. Okay, now if I return, for example, here to the picture, then we have here omega 1, it's in the direction, yeah, as we noted, let's say in mechanics 1, the moment with this double row. Then we have omega 1, it's along y direction. Omega 2, it's along z or z prime direction. We have the point P here, okay? We have the distance or the position vector to of the point P to the global coordinate system here, or origin of the coordinate system. What we have here, we have R. Now, if I take R1 here, we have now the center of the disk, okay? The position of P, yeah, we have here, it's R1, and relative to this coordinate system, X prime, Y prime, and Z prime, okay, we have here to the center of the disk, we have to take also the component here in, let's say, uh, X prime direction, also the component here in Y prime direction, okay? Now you have to make the distinction between the two coordinate system. Relative to this coordinate system, we get the frame one, and around this coordinate system, or take in consideration this coordinate system, we get the relative one. Okay, we have omega 2, of course, is along z prime direction, yeah, and we have only now to make the component, yeah, in each direction. Then we get here, as I said, EF, the frame acceleration, here EF, then the following expression here. Now coming to the relative one, we use also the same expression as before, as this one here, but the relative um, uh, acceleration, it's belong to the relative coordinate system. It means instead to use omega 1 or omega dot 1, the disk, yeah, around itself will rotate with omega 2 and not omega 1. For this, we decompose each term, okay? Then, but the relationship, yeah, stay the same. Then it means here what we have for a relative, it's equal to omega 2 vector dot cross R2 plus omega 2 cross here omega 2 cross R2. As you can see, this equation, yeah, it's analog to this one. The difference, of course, the R position is belong to fixed coordinate system X, Y, Z, and here R2 is belong to relative coordinate system X prime, Y prime, and Z prime. But it's still the same equation, okay? Now, if I develop further, and before to develop further, I have to make also the remark that here, as in the previous one, okay, this term here, it's only V relative, okay? As you have seen it here, this one omega 1 cross R, the difference is this is the frame velocity, okay? But here is the relative velocity, okay? The absolute velocity is only the sum of Vf plus V relative as we have seen it for the first question, okay? Additionally, what we have in the exercise that it said that the disk, yeah, rotate with constant angular velocity omega 2, okay? Means that this term here, omega 2, is equal to 0, not omega 2, but omega 2 dot, okay? Means that the time derivative, as it's constant omega 2, the time derivation of omega 2 will be equal to 0, okay? Now, if I look to the component, then we have here equal to component of omega 2 cross V relative. V relative, we calculated it on the first question. First question. Then we have here 0, 0, and omega 2. Okay, cross the relative, yeah, and the relative we find that it's minus omega 2 r sine alpha, omega 2 r sine, cosine, sorry, cosine alpha, and you have the third component is equal to 0. Then this is if we develop, we get the following expression minus omega 2 square r cosine alpha minus omega 2 square r sine alpha. And the third component is 0. Okay, now we have a sorry, frame acceleration, relative acceleration, and now we look to the third terms, which is the Coriolis acceleration. The Coriolis acceleration, we have seen it in the lecture. This is by definition by A, C is equal 2 times, yeah, we have seen that it's frame, yeah, angular velocity cross tau relative. Okay, now in our case, what we have, the frame angular velocity is only omega 1. That it means we have 2 omega 1 cross V relative. Okay, now this is the expression is given in general, yeah, it's always omega f. Then it means here also, if you look to the notes, that here AF is omega dot F cross R plus omega F cross omega F cross R. Okay, in our case, for this example, omega F it's only omega 1. Yeah, now if we develop further, then we get here 2 times omega 1, we said it's in the direction of y, 0, and v relative, it's minus omega 2, sorry, yeah, omega 2 r sine alpha. We have omega 2 r cosine alpha, and we have 0. Okay, now if we make the cross product, we get the following expression 0, 0, 2 times omega 1, omega 2 r sine alpha. This is the expression of uh, Coriolis acceleration. Then it means we have only now to make the sum of AF plus A relative plus AC, we will get the acceleration of the point P. Then if we make so, we get AP equal to minus omega 1 square multiplied by L plus R cosine alpha minus omega 2 square R cosine alpha. And here we have minus omega 2 square R sine alpha, and third component is 2 times omega 1 omega 2 R sine alpha. This is the expression now of the um, absolute acceleration of the point P. Okay, then we have come to determine the angular velocity, the angular acceleration of the disk D. If we do so, we have always that its expression, yeah, omega by in general, then here the angular acceleration, omega here the third point, omega dot absolute. I write it like this. This is only the derivation. This is it's equal to d divided by dt of omega. Let's say I call it I in general, yeah, projected along a relative coordinate system y. It means it's belong to this coordinate system. Then it will be here in our case, we have omega. For this example here, omega dot absolute will be the local derivation d. I make it with this symbol d over dt of omega absolute plus omega f frame cross omega absolute. That is means we make from here, we have d over dt of omega I a prime a. That is means here we will get d omega dot, but locally, plus omega I d over dt of a I prime. The second term will be only omega f, yeah, because in here we have only the frame acceleration which rotates the whole system. We have omega f, the angular velocity. In our case here, it's only omega 1, okay? And omega absolute is the combination or the sum, let's say, of two vectors, which are omega f plus omega relative. In our case, omega here, relative to this one, the two components, omega f or omega 1 and omega 2 are constant. That it means their time derivation, yeah, if I write omega absolute, it's we have the component of 0, omega 1, omega 2, okay? If I make the time derivation of it, of them, of this vector here, then in this case we will get 0, okay? Why? Because the both omega 1 and omega 2 in this exercise are given as constant, yeah? Then we have this term here, it's equal to 0, okay? Then it means we can write now, this is as component here equal to omega f will be only 0, omega 1, as is the frame angular velocity, 0, cross the absolute, that is means the omega 1 as vector plus omega 2 as vector, okay? Omega 1 is given in y direction, and omega 2 is given in z direction. Then it means what we have here, we have 0 in x direction, omega 1, and omega 2. Okay, this is what we have. Then we have only to make the product, yeah, or yeah, cross product. Then we get omega absolute here. Dot the angular acceleration. Then we get here the value of omega 1 multiplied by omega 2 and 0, 0. Okay, this is what it's asked for. Okay, then we have finished with this exercise. Now coming to the second one, okay? I have only to find, no, the second exercise here, we consider in this system represented below, yeah, we have the point A slides upward with the velocity VA, yeah, and we did want to determine the velocity VB of this point here, yeah, graphically and by calculation, yeah. Graphically, that we will use what we have done in this morning, yeah, the instantaneous center of rotation, and um, in this case, what we know only VA, okay, and here VB, we know VA, yeah, the magnitude is given here, VA is equal to 3 meter per second, okay, we have this distance, capital letter L, okay, we have this distance, small letter L, and we have at this position here, phi is equal to 30 degrees. That is means to determine VB at the position phi, which is equal to 30 degrees. Yeah. Now, if I come to the solution, okay, then it's not easy, to be honest with you, to draw on the laptop. Yeah, I prepared the solution, yeah, graphically, let's say. I'll rearrange it a little bit. Okay, I hope you can see the picture. Okay, what we have here, yeah. Graphically, that it means we don't use, yeah, let's say the expression, yeah, or let's say the equations. That's what we got. This is we do it in the second part, yeah, and to compare the two value, let's say. Graphically, it's not precise, okay? That it means it's not really approximative, but you will lose, yeah, some accuracy in the value, yeah, compared to the calculation using the equations, okay? Now what we know? We know the magnitude, yeah, the magnitude of VA, yeah. This is, let's say, it's given if we take the coordinate system X and Y, okay, VA will have the component only in Y direction. This is the magnitude VA, which is equal to 3 meter per second. Yeah. And we have now the magnitude as well as the direction. It's in y direction. Okay. Now to come to the um, center of acceleration, okay, what we know, sorry, the yeah, center of where the velocity is equal to zero. Yeah. Then we have VA. What we do, we said if we know the direction of one velocity, we make the perpendicular line to it. Okay, we have this line here. I will make it in red color, and I hope it will not confuse our solution. Then we have this line here. Okay, this is the first line, which is perpendicular to the velocity here, VA. Okay, we have the contact point, yeah, of the system. When it moves up here, the point A, this system here, it's rotating around the point C. Okay, that it means there is only one direction, which is VC. It's tangent or parallel, yeah, to the here the system, which is only sliding, yeah, it's not rotating, yeah. Then if it's like this, then we get the direction of VC also, yeah. This is, I put it here in another color. That it means we have here VC, direction of VC, and we take the perpendicular to this velocity. Then we have here the angle, which is 90 degree. Okay. Now, what we have here, we have also VB, yeah, the direction, we will see it later. What we get here, okay, intersection of two line, the intersection, we give this point here, M, and this is the center of um, uh, angular of the velocity where it's equal to zero. That is means here what we have, I write V M at this point M, okay, as vector I write it is equal to zero. Okay, this is the center. I forgot the name. Yeah, I'm sorry. Yeah, instantaneous center, yeah, of rotation here, M. Yeah, this is what we have seen this morning. Then Vm is equal to zero. What we know? We know the magnitude of Va, but we don't know the magnitude of Vc. Okay, we are looking for the velocity of the point P. Yeah, we know the distance here. What we do is the following. Graphically, we determine now, we know the position of M. Okay, what we have only to measure, yeah, or reading of the distance EM. Okay, respecting the scale, okay, we know L, small letter L. We know capital letter L. Okay. By drawing this, you take millimeter sheet, for example, then we measure here a reading of this distance AM, and also we can read CM. Yeah. If we do so, here exercise 2. Yeah. That's what we have here. VC, yeah, this is I write it graphically. What we have VC, the velocity at the point C, this is parallel to the vector or the position, let's say A, B. Okay, this is its parallel. Now calculation of VB. We know that VB here is, sorry, it's not equal here. Yeah, it's parallel. And VB here, it's perpendicular to MB. Okay, when I return back now to the picture now, what we have here, we draw the line here, MB. Okay, when we draw the line now to the point B from M, as we know it now, M, the position, we draw the line, and after this we get the direction of VB. Why? It's always perpendicular to the line joining the point M. Okay, now we can get the direction of VB. Yeah, it's only a matter of to get the magnitude. This is what we are looking for. What we know now VA is equal to omega time MA, the magnitude of the distance MA. Yeah. Why? Because we do always, we say the equations that we know in mind. Yeah. VA is only Vm plus omega cross, yeah, the position between the point M and the point A. Vm is equal to 0 because is, yeah, instantaneous center of rotation. Yeah. Then what we get here, we can get omega. It's only VA vector, yeah, let's say, sorry. This is the value VA, yeah. I make it here also in absolute, it's not vector, yeah. By what we are using here the absolute value or the magnitude, also VA will be the magnitude, yeah. Then it means here we have VA divided by the magnitude MA. VA, the magnitude, we know it is only V. It's given by 3 meter per second. This is VA, okay? And MA, yeah, we can measure it. Okay, then it means here we have VA, the absolute value or the magnitude. We measure this distance from the point M to A, yeah. You take the rule, yeah, you make the scale in centimeter, and then you will get this distance here, MA. Okay, then we can get the omega. It's sliding, but each point here, yeah, it's rotating. Now, if we make so, then we get here the value of omega. We replace it, then we get here also VB. I write here also VB. It will be the same equation. Then we have VB, it's only Vm. Vm is equal to 0 plus omega here as magnitude multiplied by the distance mb. If we replace now omega by its value here, then we get Vb, it's only Ve divided by Ma multiplied by the magnitude of Nb. Yeah, then we will find Mb. As I said, you can measure it. Ma also, V is given 3 meter per second. Then we get 242 meter per second. Okay, this is now the value. Now coming by calculation. We take now here, we have omega, it's not given. VB, it's not given. VC, it's not given. Yeah. Then we make here by calculation. If, for example, we have, for example, here, not for example, that we have here R, the distance vector position RA. Here we have only 2D problem. Then we have minus L and minus L multiplied by tangent phi. Okay, this is the vector position. That is means we have here R A, yeah, which have here the distance L Yeah. If we take here the coordinate system, and if we take here, we take here this coordinate system, put it here. What we have here, we have the angle phi, which is 30 degree. Yeah. Then we have here L cosine alpha in x direction, and we have here y direction. We have L um, sine alpha, and both, of course, here when you see the point E, both are negative. Okay. Then we get here the position. Then we know by definition VA also, as we know only this VA, we don't know other position. And as I said, the uh, instantaneous center of rotation where the velocity is equal to zero, as you can see, it's only, let's say, 90% is used graphically, yeah, without calculation, okay? Or only if it's asked for, then you have to do this. Now, what we know RA, yeah, dot. This is the time derivative of the uh, vector position, yeah? VE, it's only R, the vector position, we make the time derivative. Now, if we do so, what we have the angle phi, yeah, and phi now, okay, at this position, 30 degree, of course, when it's sliding, yeah, up, then in this case, that's what we have phi at each point here will change with the time, okay? That it means there is phi dot, okay, but L here is constant, yeah, doesn't depend on time. Then its derivative, yeah, it's there. Now, if we look to the second term here, what we have minus L dot, which is equal to zero tangent phi, yeah, and plus minus L time derivative phi dot and the derivation of tangent phi. Okay, then we get here minus L divided by cosine square phi multiplied by phi or phi dot. Yeah, this is the expression of VE. Then it means here we have, if I take now the absolute value, when we get here, we get VE. VE has two components. Yeah, it's given in y direction. In x direction, it's equal to zero. That is, means we have here zero VE as value, and here it's zero, of course, which is logic, minus L divided by cosine square phi multiplied by phi dot. Okay, this is what we have. Then we can make the equality here. Zero must be equal to zero. There is no contradiction. And VA will be equal to this term here. Okay, the value VE is given. The angle phi is given 30 degree. L is given. Phi dot, we don't know the value. Okay, then we can determine now phi dot. It's equal to minus VA divided by L cosine square phi. Yeah, this is what we get for phi. Okay, but it's asked to determine the value of VB. Yeah, then what we have, if we calculate now the position or describe the position in X and Y direction of RB, now we have here R of the position B. This is will be equal. And now if we look to the point B here, okay, and we look to this position here, what we have the distance L here with here it's positive, yeah, with the position that is means we have this distance here projected L along X direction minus small or small letter L here, okay, and the same for here for Y direction. Okay, we make the projection of L, okay, along Y direction and minus this distance here too. Okay, then we get here L cosine phi minus L, and we have along Y direction L sine phi minus L tangent phi. Now, if we look to RB and VB is the same, we use as this equation here, it's only RB dot, okay? Then we have here VB, it's R dot B, and then we have here, if we derive with respect to time, we have minus Al sine phi multiplied by phi dot, and we have here L cosine phi minus L multiplied by 1, or I make it better here, minus L divided by cosine square phi multiplied by phi dot. And this is the first component here, and this is the second component of time derivation of vector position in B. Then we will get, we replace here, of course, phi dot by its value here. We have to replace it here, or substitute it, the value here, phi dot. Then we get that VB will be equal to L divided by small l VA multiplied by sine phi multiplied by cosine square phi, and VA multiplied by 1 minus L divided by L cosine cubic phi. This is the expression when we replace phi dot by its value. Then if we replace the value of each term, L, capital letter L, small l, VE, and so on, then we get here 2, 3 minus 0.9 and meter per second. Then in this case, we get VB as magnitude equal to 2.47 meter per second. This is the value of VB, which is asked for. And you see, this is the exact value, 2.47. And graphically, as I said, it's only approximation. It's 2 here, dot 42, yeah. Okay. This is the second exercise. For the third one,